Okay, welcome to AS-Chemistry, Paper 1, Inorganic and Physical Chemistry. This is the specimen materials set to paper walkthrough. So pause the video, have a go at the question, and then unpause the video and watch the answers. This question is about a toxic chloroalkane X that has a boiling point of 40 degrees. A student carried out an experiment to determine the MR of X by injecting a sample of X from a hypodermic syringe into a gas syringe in an oven at 97 degrees and 100 kilopascals. The student's results are set out in table 1 and 2. So we've got 10.340 grams before injection and 10.070 grams after injection. We've also got a volume reading of 0 before injection and a volume reading of 105 centimeter cubed after injection. And 1.1 says complete table 1 and 2 by calculating the mass and volume of X. So for the first one, we do 10.340 minus 10.070 and we get 0.270. And for the second one, it's really simple. Before there was nothing, after 105. So the volume is 105 centimeter cubed. Right, let's move on. Here's the calculation, 5 marks. X is known to be one of the following chloroalkanes: CCl4, CHCl3, CH2Cl2, or CH3Cl. Justify this statement by calculating a value for the MR of X. Use your answer to suggest the most likely identity of X from the list above. Give your answer for the MR of X to an appropriate precision. The gas constant R is equal to 8.31 joule K mole to the minus 1. All right, well, I'm bringing the information down from above so I don't have to keep scrolling up and down. So the mass was 0.270 grams, the volume was 105 centimeter cubed, the temperature was 97, and the pressure was 100 kilopascals. So R is 8.31, which is so once you get all this information, volume and R 8.31, you know you're doing the ideal gas equation. We want the MR, so we want to rearrange the ideal gas equation to find moles, and then whack moles into the mole equation, which is mass is moles times MR. Rearrange that to find the MR. So we're using two equations here. This is often the case with the ideal gas equation. So what we're going to do, we're going to rearrange first of all PV equals nRT, and we're going to do that by going, right, I need to make N, which is moles, the subject. So rearrange to find M. We're going to do PV divided by RT, and that's going to give us N. So we've got pressure times volume over the gas constant times the temperature change equals the moles, and pressure was 100 kilopascals. Now, in this equation, you've got to turn kilopascals to pascals, and you just have to memorize that. So it's 100,000 pascals times 105 centimeter cubed, which we have to turn to meters cubed, because in this equation, volume is in meters cubed. So we're going to divide 105 centimeters by 1 times 10 to the 6, which is a million, and that will turn it into meters cubed. We're then going to divide the PV, pressure and volume, which we've just done above, by 8.31, which is R, the gas constant, multiplied by the temperature in Kelvin. So that's 97 plus 273. And that is going to equal 341 times 10 to the minus 3. And that's our moles. So we've now worked out the moles, and we now need to rearrange, we need to rearrange the M over MR and N by doing mass divided by the moles we just calculated. So we'd have secured 3 marks up to this point. So we now need to do the mass, which was 0.270. We need to divide that by the moles, which was 3.41 times 10 to the minus 3. And this is going to give us the MR. And our MR is 79.1. And so that is X. Now you'd need to look up in the periodic table. No, you wouldn't. You would need to calculate the mass of these 4 compounds we've been told it could be one of. Which one is closest to 79.1? When I said look up in the periodic table, you'd need to do that to find the mass numbers of all of these. So the first one is 12 for the carbon plus 4 times 35.5 for the 4 chlorines. That comes to about 154. I might have got this wrong. Check it out in your calculator, but it's way off of our 79.1 that we calculated. So that's not going to be the identity of X. The second one is CHCl3. So we've got 1 carbon, 1 hydrogen, and 3 times 35.5. Again, this is going to be way off you can see straight away with 3 times 35.5 is going to be bigger than our 79. And it's 119.5 or thereabouts. Again, you might need to check that with your calculator. Now, if we look at the third one, we have a formula of CH2Cl2. Now that's going to be 12 plus 2 for the two hydrogens is 14. And then 35.5 times 2 is 71. 71 and 14 is 85. So actually, this one is starting to look a little bit better and is quite close. So we're going to say the identity is CH2Cl2. And for the final one, you've got a methyl group, which is 15 plus 35.5. That's like 50.5. So it's way off, way below our predicted MR. So the MR is 79.1 and the identity is CH2Cl2. And that will get you 5 beautiful marks. All right, let's move on. Keep moving on, keep moving on, keep moving on, keep moving on. Suggest a reason other than apparatus inaccuracy why the MR value determined from the experimental results differs from the actual MR. Explain your answer. So, why would the MR value that we determine from the experimental results differ from the real MR? And there's a couple of different reasons that this could happen. We did PV over RT equals moles. Now, if the volume was too big because we injected extra air into the syringe or something like that, then what would happen is we would get a larger amount of moles. And that is then when we divide the mass by the MR, by the moles to get the MR, we would get a smaller MR than expected. So if we overcalculate the moles because we inject a bigger volume, so when we do PV over RT, we get a bigger N, then that means when we do M over N, N is bigger and we get a smaller MR. However, there are alternatives as well to this. So it could be that when we injected the syringe, not all of it got injected and the volume could have actually been smaller. And in that situation, we get a underestimation of moles. And then we would do mass over moles and we get a larger MR than expected. So it could have been either way why you get an inaccuracy in your MR. It could be that you've got too much volume, which results in a smaller too much volume, sorry, which results in a larger amount of moles. And then as you can see there, I've drawn the arrow up and arrow down, and then you get a smaller MR. So that's one version. And then the other version is if we didn't inject enough in, we get a smaller volume. And with a smaller volume, we would get an underestimation of the moles and therefore an over calculation of the MR. Okay, let's look at 1.4. Suggest with a reason and appropriate safety precaution the student should take using the toxic chloroalkane X in the experiment. Well, if it's toxic, it's going to give off toxic vapors. Most organic compounds give out vapors. Use a fume cupboard because those toxic vapors are dangerous. You won't get them marked for saying goggles, lab coat, or gloves because it's the vapors from the organic solvent that are dangerous. Right, the question is about enthalpy changes. Write an equation including state symbols to show the reaction taking place when the standard enthalpy of combustion of ethanol is measured. So we want 1 mole of ethanol being combusted completely in oxygen to form the products. So we've got ethanol C2H5OH, liquid, plus oxygen. I'll explain why I've put a 3 there. It's gaseous oxygen, and that is going to form carbon dioxide and water, just like all other complete combustion experiments. So why do I need 2 carbon dioxides? Well, because there's 2 carbons in the ethanol. Why do I need 3 waters? Because there's 6 hydrogen atoms in the ethanol, which means 3 times H2. So I need 3 waters, 3 water molecules. And that's why that's balanced like that. And if you add up the oxygens on the right, you've got 2 times the O2 in carbon dioxide and 3 times the O. So we need 7 on the other side. There's 1 in the ethanol and 3 in the O2. 2.2, state the name given to the enthalpy change represented by the following chemical reaction. Explain why the enthalpy change would be difficult to determine. So this is the enthalpy change of formation because we've got the elements in their standard states under standard conditions. All right. Okay, so carbon is a solid, oxygen's a gas, forming carbon monoxide. The problem is carbon monoxide is highly reactive and would rapidly form carbon dioxide with touching any oxygen in the air. So unless you have a way of limiting the supply of oxygen perfectly, you are not going to be able to carry this out. So it's going to be very difficult to measure directly. So what we can use instead is a calculation. So we've got the standard enthalpies of combustion for carbon and carbon monoxide are minus 393 kilojoule per mole and minus 283 kilojoule per mole respectively. Use this data to calculate the enthalpy change for the reaction in 0.22. So really we want to do the bonds broken minus the bonds made. So we're going to break the bonds in the carbon and then we're going to reform them into the bonds in the carbon monoxide. So what we want to do is minus 393, which is for the carbon, which is where we're going to break all those bonds. And then we're going to subtract the products or the bonds made, which is going to be in the carbon monoxide. So minus 283 kilojoule and per mole. And that's going to give us the enthalpy change. And that is going to be something like minus 110, minus 110 kJ per mole. Awesome. Now let's move on. 2.4. Use the following data to calculate a value for the XEF bond enthalpy in XEF4. So that's xenon, by the way, that element, and fluorine. So we've been given the data for Xe plus 2 fluorine molecules goes to XEF4. We're trying to find the bond enthalpy for one XEF bond. Okay, we've got the data here when fluorine reacts with Xe to make that. However, we also need to look that in order to form fluorine, we need to join together 2 fluorine atoms in the gaseous form. Now, as we're reversing the sign down below, this plus 158, we're going to multiply that. So it's plus 316, and then we're going to reverse the symbol because we're going in the other direction. So this is now, we're going to reverse the symbol so that it's exothermic rather than endothermic. So it's going to become minus 158 times 2, which is minus 316. And then we've got, if we follow the arrow round and go in the right-hand direction with the top one, we have minus 252. So put them together and we're going to get 568. And then we're going to divide that by 4 because there's 4 XeF bonds. And we're going to get 142 kilojoule per mole as the bond enthalpy. And there we go. Okay, question 3. Magnesium exists as 3 isotopes, magnesium 24, 25, and 26. In terms of subatomic particles, state the difference between 3 isotopes of magnesium. Well, really easy. They've all got different amounts of neutrons. Okay, so magnesium 24 has 12, 25 has 13, and 26 has 14. What differences will there be in these isotopes in terms of chemical properties? Well, there'll be no difference because they've got the same electronic configuration. You could say the same amount of electrons in the outer shell. Right, we've got a difficult one here and a relative atomic mass equation. Magnesium 25 makes up 10% of the mass in a sample of magnesium. It has an AR of 24.3. Use this information to deduce the percentages of the other 2 magnesium isotopes. So essentially we're looking at the sum of the isotopic mass times the abundance for each of the isotopes divided by 100 is going to equal the AR of 24.3. So I know that 25 times 10 is the mass and the times the abundance of the first one. I then know that magnesium 24 and magnesium 26 combined must equal 90%. So we can make an assumption that the abundance of magnesium 24 is X, and therefore the abundance of magnesium 26 is 90 minus X. Now, just to explain what that means, imagine that the abundance of magnesium 24 is 8%, so X is 8%. Then the abundance of magnesium 26 would be 90 minus 8, which would be 82%. But what I'm going to do is I'm going to get rid of the 100 that we put underneath, and we're going to times both sides by 100. And if we do that, multiply both sides by 100, we're going to get 2,430 on the right. And we're going to take the 100 away from underneath. I'm then going to multiply 25 by 10, multiply out the brackets. And we're going to multiply 26 times 90 to get 2,340. And we're going to multiply 26 by minus x to get minus 26x. We're then going to simplify on the left-hand side by going minus 26x and 24x equals minus 2x. And I'm left then with 250 plus minus 2x plus 2,340 equals 2,430. Now I need to add all the numbers together. So I'm going to get 250 plus 2,340. I'm going to get 2,590 plus minus 2x is equal to 2,430. Now I want to get x on its own. So I'm going to subtract the 2,590 from both sides. And I'm going to be left with minus 2x equals minus 160. What do we do then? Well, we need to find out what x is. So we're going to go minus 160 divided by minus 2. And that is going to equal 80. So x is 80. So magnesium 24 has an 80% abundance and magnesium 26 has a 10% abundance. Now you could have got these the other way around. It depends which one you assume is x at the start. Superbulous. Let's move on. Keep moving on, keep moving on, keep moving on, keep moving on. Okay, let's go. 3.4. This is a time of flight mass spectrometer. Ions are accelerated to the same kinetic energy. We have the equation K equals half mv squared, where mass is in kilograms, velocity is in meters a second to the minus 1. V equals d over t, where d is distance in meters and time is t in seconds. Now in this question, it says a TOF mass spectrometer. Each magnesium 25 plus ion is accelerated to a kinetic energy of 4.52 times 10 to the minus 16 joules, and the time of flight is 1.44 times 10 to the minus 5 seconds. Calculate the distance. So we want to rearrange v times t so that it equals d. We can calculate the distance. We also need to rearrange the kinetic energy equation so that we can find velocity. Once we have the velocity, they've given us the time, times the velocity by the time, and you'll get the distance. Why don't you have a go, and then I'll go through the answers. Right, let's get into it. So first thing I want to do is take this kinetic energy equation, and I want to rearrange it to make velocity the subject. So I'm going to times the kinetic energy by 2. Let's just set this out properly for you. So remember that kinetic energy is equal to half mv squared. So I want to get rid of the half. So how can I get rid of that? There's two ways, but the way that everybody seems to prefer is to times the kinetic energy by 2. And then you're left with 2ke equals mv squared. Now I want to leave the v squared on its own. So I'm going to divide 2ke by m. And that's going to leave me with v squared. Now I want to get rid of the squared. So I'm going to do the square root of 2ke over m, and that will equal v. If I can get the velocity, then I can just times it by the time, and we'll have the distance. So we're going to do 2 times 4.52 times 10 to the minus 16, because that was the joules, that was the kinetic energy. Now I want to divide it by the mass. Here comes the tricky bit. The mass, well, we know the mass of one ion is 25. That's its mass number. But what does that tell us? Well, the mass of an ion is 25, but that's 25 grams per mole. What did we say earlier? We need the mass in kilograms. So the fact I need the mass in kilograms, I need to do 25 divided by 1,000, which is going to get me the mass in kilograms, which is 0.025 kilograms. Now, I've just worked out the mass of 1 mole. That's 6.022 times 10 to the 23 atoms. Right, it's a lot smaller than that. I need to find out how much just one ion, what's the mass of one ion. So I've got to take my 0.025 kilograms and divide it by L. L is Avogadro's constant, which is how many ions are in 1 mole. So I've got to do 0.025 kilograms, which is the mass of a mole, and I've got to divide it by 6.022 times 10 to the 23. And what we'll do by doing that is find out the mass of one ion, and it's going to be a really small number. Okay, you're looking at the mass of an ion, and it is 4.15 times 10 to the minus 26. So let's take our 2Ke and divide it by this mass. So 2 times 4.52 times 10 to the minus 16 divided by 4.15 times 10 to the minus 26. And we've now got to square root that answer, and we'll get the velocity. Now, let's not forget we've just divided the joules in kinetic energy by the mass and then square rooted it to get the velocity. And what we find is we end up with 2.17, you could call it 2.18 times 10 to the 10. Let's round that. And we square root that, and we're going to get the speed. Now, how fast is this ion going to be traveling? It's going to be traveling a pretty hefty speed. So our velocity of the one magnesium 25 plus ion is 147565.416 meters a second. So it's basically doing 147,565 meters a second. We've got its velocity, right? Now we need to multiply the velocity by the time, which was 1.44 times 10 to the minus 5 seconds, I believe, minus 5, or is that minus 3? My eyes are deceiving me. And if we times the velocity by the time, we're going to get the distance of the tube. And then you've got to say, is this practical? This person is using a time of flight mass spectrometer. That's in a science lab. If you get 20 meters, 30 meters, 100 meters, that's too big. But we've got an answer of about 2.12 or 2.13 meters. And that makes about sense because it's a wiggly curved tube on the machine. And that makes sense. And that's your answer. 4 marks. Boom. Okay, moving on. Question 4. A sample of strontium ore is known to contain strontium oxide, strontium carbonate, and some inert impurities. To determine the mass of strontium carbonate present, a student weighed a sample of the solid ore and then heated it in a crucible for 5 minutes. The sample was allowed to cool and then reweighed. This heating, cooling, and reweighing was carried out 3 times. The results are set out in Table 3. So we have the mass of the crucible, and the ore, and then we have the mass in the crucible after each of the 3 times heating, where you can see obviously the mass has gone down to 14.66, 14.58, and then 14.58 a second time. So we've heated until a constant mass. When the strontium carbonate is heated, it decomposes according to the following equation. First thing to notice about equations is the ratio. That's normally the really important thing to see. So we've got, it's a 1-to-1 ratio going on with, so that's going to might be important later. I always like to note that down. The first question is, give a reason why the mass of the solid sample changed during the experiment. So they're heating a carbonate. What gets given off when you heat a carbonate? Well, it's been shown here. We've got solid and it gives off the gas carbon dioxide. So we're losing mass because we're losing the carbon dioxide gas, which is escaping from the crucible. And that's a nice, easy first mark. Okay, let's move on to the next part of the question. 4.2, use the data in the table to calculate the mass of strontium carbonate in the original ore sample. Okay, so we want to calculate how much strontium carbonate was in the original ore sample, and we want to do it to the appropriate precision. So we're going to do that up here. So essentially, how much strontium carbonate in the ore, or the original ore, strontium ore. Okay, let's have a little look. So mass of the crucible was 9.85. Nice. The mass of the ore, therefore, is 16.11, take away the 9.85. This is before we've heated and broken down the carbonate into oxide and carbon dioxide. So we now know that we had a 6.26 grams of ore in total, of strontium ore. Now, of that, how much carbon dioxide came off? Well, we got it down to a constant mass when it went to 14.58. So that means how much carbon dioxide came off? 16.11 minus 14.58. Whack that into the calculator. Bada bing, bada bong. 1.53 grams of carbon dioxide. Now remember I said about the moles and the ratio? We're going to work out the moles of carbon dioxide and therefore we'll know the moles of strontium carbonate in the original sample, as it's a 1-to-1. So moles of carbon dioxide is mass over the MR. The MR of carbon dioxide is 44. You probably know that off by heart by now, but 12 for the carbon, 32 for the O2. So 44. And that equals 0.0347 moles of carbon dioxide. And so we can round that to, it's actually 0.03477 something. So I can round it to 0.0348 if I want here. And as I know it's a 1-to-1 reaction, we know that our strontium carbonate is also going to be 0.0348 moles. Now what we can do is work out the MR of strontium carbonate and do MR times moles, and we'll get the mass of the original strontium carbonate. So what is the MR of strontium carbonate? Hold on. I've written 0.0345. I meant 0.0348 moles of strontium carbonate. Now I need to multiply that by the MR of strontium carbonate. So we're going to take our carbon, which is 12, our oxygen, which is 16. We're going to whack that all together with the strontium. You'll find in the periodic table it's 147.6. Times that by 0.0348, and you're going to get 5.13 grams of strontium carbonate. And that is the mass of strontium carbonate in the original ore. Okay, let's move on. Hope you're liking the walkthrough so far. If you are, make sure that you hit the old like button, please. Right, 4.3. Each balance had a reading, an uncertainty of plus minus 5 milligrams. Calculate the percentage error in the initial mass of ore used. So we've got to do a little equatione here. And we used two readings to come up with the initial mass of 6.26 grams. Remember, we used the 9.85 and the 16.11. So there were two lots of percentage error. So actually the total percentage, the total uncertainty, not percentage error yet, is 5 over 1,000. Let's convert that into grams first of all. So the uncertainty is 0.05 grams in each of our readings. Why do we need to convert it into grams? Well, because our masses were in grams. But remember that we've got to times it by 2 because we did a reading at 9.85 and a reading at 6.11. And then you take the percentage error is the uncertainty total, which is 0.01, over the measurement, which was 6.26, times 100. And you get 0.159. or 0.160. I hope that was clear. If it was clear as mud, put a thumbs down. Oh, wowza, that was my mum calling me. 10 o'clock at night. What can you do? So here I am combining the two levels of uncertainty for each of the measurements, one at 9.85, one at 16.11. Okay, let's move on. 4.4. The mass of inert impurities in the sample was 347 milligrams. Deduce the mass of strontium oxide in the sample and justify any assumption made in calculating your answer. So we know the total mass of the ore was 6.26 grams. We know the carbonate was 5.13 grams. So guess what? We can work out that there are 1.13 grams left over. Of that, 347 milligrams is impurity, so it can't be the strontium oxide. So what we want to do here is do 1.13 grams minus the impurity. That's 347 milligrams, but essentially you divide that by 1,000 to put into grams. So you're basically doing 1.13 take away 0.347 grams, and you get your final answer, which is 0.783 grams. And that must have been the mass of the strontium oxide in the original strontium ore. Super. Hope that was good. Let's move on. Make sure you pause the video before you try each of these questions, and hit the like button, guys. It helps with the channel, helps with the whole algorithm. Do, 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 do. Right, let's go. 4.5. Strontium metal can be extracted by heating strontium oxide with aluminium metal. In this reaction, strontium vapor and solid aluminium oxide are formed. Write an equation for the reaction and state the role of the aluminium in the process. Explain why the strontium forms a vapor, but aluminium oxide is formed as a solid. I like to use a highlighter to highlight key points of the question here. Anyway, enough waffle. Let's get on and balance this equation. So we've got strontium oxide, which is a solid, plus aluminium, that's a metal, solid. Form strontium vapor, so it must be a gas. Vapor means gas. And aluminium oxide. Formula Al2O3. Because aluminium is a +3 ion, it's going to join with 3 oxygens. Right, check the oxidation states to see what the role is of aluminium. Well, you can see here it goes from 0 as an element to +3 when it's joined with oxygen. So it lost 3 electrons, which means the aluminium was oxidized, but that's not its role. Its role is therefore a reducing agent because it took some electrons. And so it gave away some electrons and made something else reduced. So that is why the aluminium is a reducing agent, because it loses electrons, itself is oxidized and gives electrons away. Oops, I just noticed I haven't balanced this equation up here. Let's balance this equation. So we have 2 aluminiums in the aluminium oxide, so I need a 2 next to the Al, and I'm going to need 3 oxygens there, so I need a 3 by strontium oxide. That's balanced. Lovely jubbly. Right, let's get on to this explanation. So the last bit of it is that we've done the role of aluminium. Explain why strontium forms a vapor, but the aluminium oxide, because it's obviously very hot for the metal to form a vapor, but why does the aluminium oxide stay as a solid? Well, strontium's a metal. It has metallic bondings. You remember from GCSE, that's formed by electrostatic attraction between positive metal ions and delocalized electrons. This is going to be weaker by this very information here. This must be weaker or require less energy to overcome than the bonding in aluminium oxide. Aha, so what bonding do we have in aluminium oxide? Well, it's a giant ionic lattice. So aluminium oxide has strong ionic bonds, which means we have strong electrostatic forces of attraction between oppositely charged ions. In essence, what we're being shown here is that metallic bonding is relatively weak compared to ionic bonding. Now, metallic bonding is quite strong. Most metals are solids other than mercury at room temperature, but we're getting the impression here that it's not as strong as ionic bonding. Okay, let's move on. We're on question 5. A student was given a 50-gram sample of solid silver chloride contaminated with solid silver carbonate. The student suggested the following method to obtain the maximum amount of pure dry silver chloride from the sample. Tip the solid in a boiling tube, add dilute nitric acid, allow the remaining solid to settle, decant the liquid, leave the sample to dry. Identify any faults or omissions in the method suggested by the student. Suggest improvements using commonly available laboratory equipment. The following chemicals are also available. We've got distilled water, dilute solutions of sodium hydroxide, ammonia, hydrochloric acid, and sulfuric acid. First off, 50 grams might not fit in a boiling tube, especially once you add the acid in, the nitric acid. So better to use a beaker instead. So what have we done here? We've identified a fault, which I've put in red, might not fit in the boiling tube, and then highlight this in green, use a beaker instead. So really, to get the 6 marks here, you want a minimum of 3 errors with the corrections. Let's have a look at another one. So what else have we got? They haven't said the volume of acid. They've just said add dilute nitric acid. They haven't given us a volume. So no volume of acid given. We need to use excess acid to ensure that we have reacted all of the silver chloride. Oh, sorry, to ensure we've got rid of all of the carbonate. Now, how will we know that's happened? We'll know we've got rid of all the carbonate when all of the carbon dioxide bubbling stops. So you're going to keep adding nitric acid until the bubbling stops. So no volume of acid given. We need to ensure excess. Decanting, what is that? That's when you have a liquid floating on top with some solid at the bottom and you tip the liquid off. This means that the solid is still going to be wet, not properly dried. So what you should do is wash it with distilled water, filter it, rewash, and then dry it. Okay, so I'm just highlighting the mistakes in red and then highlighting the improvements in green. Is there anything else? Let's have a look. What else have we missed here? Ah, so another error here is they've used nitric acid. Now, nitric acid is not a good thing to use because the nitric acid, you'll know from your halide ion tests, nitric acid will react with silver to form silver nitrate. Remember, we use silver nitrate when we're doing the precipitation test for halides. So we're going to get some silver nitrate formed, AgNO3. What does that mean? That means some of our silver is going to disappear and we're going to lose some of our silver chloride. We're not going to get the maximum amount of silver chloride produced. So we should use, the improvement here is to use hydrochloric acid instead. And that way you won't lose any of your silver chloride. You'll get the maximum amount obtained. So instead of using nitric acid, the improvement is use HCl instead. Okay, let's move on to the next question. So we just finished that 5.1, which was a nice 6 marker, and now we are moving on. Okay, let's go. Question 6. The question is about elements in group 7 of the periodic table and their compounds. Bromine, strontium chloride, iodine monochloride all have similar MR values. Suggest with reasons the order of the melting points for these three substances. So bromine is the lowest melting point as it is a simple covalent molecule. As you remember from GCSE, simple covalent molecules only have weak intermolecular forces. At A level, we can call them dispersion forces, London forces, or van der Waals forces. So it's only got those weak van der Waals forces. Why did they tell us they've got similar MRs? Because van der Waals forces get bigger when you have different sized molecules. The bigger the molecule, the more van der Waals forces, the more electrons, the more van der Waals forces. So by the question telling us they're all the same, they're telling us the van der Waals forces are the same with all of these. So ICl has the next lowest melting point, and that's because it has a permanent dipole-dipole. Okay, so that's because chlorine is much more electronegative than iodine. It's higher up and further to the right in the periodic table, so it forms a permanent dipole. And so in between the molecules are dipole-dipole forces. And that is because they're called dipole-dipole because if you draw two of the molecules out like I have here, you've got two dipoles and the forces are in between those dipoles. Now it's not quite as strong as ionic bonds. So the one with the highest melting point is strontium chloride. It's a metal and a non-metal. So it's going to have a giant ionic lattice, lots of strong ionic bonds. Remember, that's the electrostatic attraction or strong forces of electrostatic attraction between oppositely charged ions. They're going to require a lot of energy to overcome, which is why our ionic compound has the highest melting point. And there we go. That'll get you your lovely jubbly 6 marks. I do like those kind of questions. Nice and easy bankers. You want to make sure this is a terrible drawing of an ionic compound. Pay no interest to this. I don't know why I'm bothering with that. Right, let's move on. 6.2, write an equation for the reaction of chlorine with cold water. This comes up a lot. State a reason why chlorine is added to drinking water and suggest the disadvantage of treating water in this way. So the equation is Cl2 plus H2O, reversible reaction. We get two acids formed. We get hydrochloric acid and hydrogen chlorate. Okay, what's the reason? Well, it kills bacteria, sterilizes the water, so that's why we add chlorine. Chlorine's toxic, but that's not the disadvantage. It's that it can cause irritation. When you go swimming without your goggles, your eyes hurt. Also, although you don't go swimming in your drinking water, it also might affect taste negatively. So some people don't like the taste. And also it can react with organic compounds, things like your plastic water bottles that you put your tap water in. Okay, 6.3, bromine reacts with phosphorus to form phosphorus tribromide. Write an equation for this reaction and draw the shape of the phosphorus tribromide molecule formed. Suggest the bond angle in the phosphorus tribromide. Well, we know that bromine is Br2. It's a halogen. It's diatomic, so it comes as Br2. So we want to write Br2 plus. We know the symbol from our periodic table for phosphorus is P, so we're going to write P. And therefore, we would normally think, well, phosphorus tribromide must be PBr3. Tri means 3, so PBr3. And then we balance this, go 3 there, 2 there. Lovely jubbly. Surely that's the marks. Actually, it's wrong. Da-da-da-da. And that is because phosphorus, and you just have to know this, but phosphorus comes as P4. So it forms a little structure where there are 4 phosphorus atoms when it's in its elemental form. You get other ones like sulfur that forms one with 8 sulfur atoms sometimes. It can form ones with 6 and other ones. So you just have to know that phosphorus comes as P4. So this is the correct equation. Okay, there are other situations like this with sulfur, silicon, I don't know, there's some other ones. Let's move on. Well, yeah, sulfur's the other one you've got to know comes as S8 sometimes. So let's do the shape. So when we're working out the shape of this molecule, okay, phosphorus is in group 5. That tells us it has 5 electrons around the central atom, so 5 electrons in its outer shell. It's bonded to 3 bromines, so we're getting 1 electron from each of those bromine bonds. So there's a total of 8 electrons around the central atom. We want to find out how many pairs of electrons does that make. Well, 8 electrons, divide them by 2. We've got 4 pairs of electrons around the central atom. Now we know there's 4 pairs, we need to know, are they all bonded? Well, we know from Br3 that 3 are bonded. That means we've got 3 bonded pairs and 1 lone pair. So it's going to form this structure here, which is like a tetrahedron, but where you've taken off the top one. So this is known as pyramidal or trigonal pyramidal. You get extra repulsion because of that lone pair. So the bond angle is slightly smaller than it would be with a normal 4 pair. 109.5 is what we get with a tetrahedral structure. But for every lone pair, you minus 2.5 degrees. So because there's 1 lone pair here, instead of a bonded pair, we're going to reduce that to 107. So the bond angle is 107 and the shape was pyramidal. Now for this next one, phosphorus pentabromide in the solid state consists of PBr4 plus and Br minus ions. Draw the shape of the PBr4 plus ion and suggest its bond angle. So we're going to go through the same routine here. We're drawing PBr4 plus. And so what we want to look at again is phosphorus is in group 5, so we have 5 electrons. It's bonded this time to 4 bromines. That should make 9 electrons. However, there's a plus sign which cancels out one of the electrons essentially. So it's got 1 less electron. So essentially we have 4 electrons around the phosphorus and 4 being donated from bromine bonds, making a total of 8 electrons. Divided by 2 to get the pairs, we have 4 pairs of electrons yet again. Are there any lone pairs? Well, you do your pairs of electrons, subtract the bonded pairs. 4 minus 4 is 0. There are no lone pairs because all of the pairs are locked up in bonds. So as there's no lone pairs, because the bonded pairs is equal to the total number of pairs, 4 and 4, we're going to have a tetrahedral structure. So a bit like the last one, but we haven't got that extra repulsion because bond-to-bond repulsion, bonded pair to bonded pair repulsion is less. So we've got a slightly bigger bond angle. We've got the 109.5 bond angle for this tetrahedral shape. And the 109.5 is the bond angle. And there we go. Don't forget your brackets and your little plus sign because it's an ion. Now we're going to do the multiple choice section. Let's get into this. Sometimes I forget to do this on my walkthroughs and I put ticks or crosses on the what I think is the correct answer. You are supposed to color in the little circle in AQA, and if you put a cross, that means you got it. You did an answer that you weren't happy with, so you can cross it out and move on. So the answer here, you can just look this up in the block. Yttrium, what what block of the periodic table is it in? Well, it's found in the D block. We can look that up in a periodic table and see that really easily. Okay, question 8. Which of the following is the correct statement about the trend in atomic radius across period 3 of the periodic table? Well, the radius decreases because as we go across the periodic table, you're gaining 1 proton with each element across. So the nuclear charge is increasing, but electrons are being added to the same shell. and so we're not getting any more shielding, so the radius gets smaller. Let's go to question 9. A measuring cylinder has an uncertainty of plus 5 centimeter cubed. What is the minimum volume of liquid that can be measured if the percentage error in the volume is to be less than 0.2%? So what we need to do here is write out the equation for percentage error. Percentage error is equal to the total uncertainty divided by the measurement times 100. So we just need to rearrange this, and we're going to have 0.2%. Whoopsie. Yeah, so 0.2% is equal to the total uncertainty, which is going to be 5 centimeter cubed, um, over our unknown measurement times 100. Now, one of these is the correct measurement. Change all of these into centimeters cubed because our uncertainty is in centimeters cubed. And then you could just one by one put them into that equation where I put the question mark. And if you do that, you'll find that 2,500. If you go 5 divided by 2,500 times 100, you get 0.2. So the answer is C. You could rearrange the equation if you wanted, but I found it even quicker just to whack those 4 different answers in and see which one fits. 10. Element Q forms a sulfate with a formula QSO4. Which of these could represent the electronic configuration of element of the atom Q? Well, Q must be +2 as sulfate is -2. So Q must lose 2 electrons. So which of these formulas will lose 2 electrons? Well, it's going to be the Ne3S2. You might say, why isn't it D? Because D is 3s1, 3p2. Well, because it's only got 1 in the S, it's going to be harder to remove the 3p one there. Which equation represents a reaction that does take place? Well, what you have to do is, this is a halogen reaction, and we know that the more reactive halogen displaces the less reactive halogen. And in this answer A here, we've got chlorine plus sodium iodide. Chlorine's more reactive, so we'll displace it. Bada bada bing. Which change would increase the yield of RM2? Well, first of all, let's look. A change in pressure to 150 kilopascals, that'd be reducing the pressure. Well, a decrease in pressure from 200 to 150 kilopascals would shift the equilibrium to the left, which would decrease the yield. Why would it shift it to the left? Because it goes to the side with the least gas molecules. Doubling the volume, which is this bottom one here, would decrease the pressure as well. So would again shift it to the left where there's more gas molecules. Then we got to look at change the temperature to 293. Well, that's a decrease in temperature from 393 to 293. It's endothermic. So if we decrease the temperature, it's going to go to the exothermic side. So that won't be right either, because if we decrease the temp, Le Chatelier says is going to try and do the opposite and increase the temp. So it's going to go to the exothermic side, which is the left-hand side, not the yield side. So we're only left with one answer, which is to remove RM2 as it is formed here. That would increase the yield of RM2. And of course, it would cause a shift to the right, because if we decrease the concentration of RM2, more M2 and R will combine in order, by Le Chatelier's principle, to counter that change. And so it will shift to the right. Lovely jubbly. Okie dokie, just 8 more of these to go. Which of these shows nitrogen in its correct oxidation states in the compound given? Well, we've got, let's have a little look here. In ammonia, it would be -3. Yeah. So in ammonia, it'd be -3 because essentially hydrogen's +1, so it needs to balance out. In this second molecule, N2O, the oxygen's always -2 unless it's with fluorine, so it's going to be +1 in that. And then over here in NHO2, it's going to be +3. You always base your oxidation states on the fact that oxygen is -2. So the answer is B here. Right, let's move on. 14. What is the volume of 0.2 mole per decimeter barium hydroxide aqueous required to neutralize exactly 30 centimeters of 0.1 mole per decimeter HCl aqueous? I need to write an equation because we need to look at the ratios. With moles, always write an equation if you can. So barium hydroxide plus hydrochloric acid, it's a simple neutralization. It's going to form barium chloride plus water. Okay, because we've got alkali and an acid. Balance it up. Aha, we have a 2-to-1 ratio of hydrochloric acid to the barium hydroxide. Now we look at the information we've been given. Um, we've been given 30 centimeters and zero point 0.1 moles of HCl. So let's turn the centimeter cubed into decimeters. 30 divided by 1,000. Let's times it by zero point 0.1 because we know that volume times concentration equals moles. So we get 0.003 moles, and that is of hydrochloric acid. So how much barium hydroxide must we have? Well, it's a 2-to-1 reaction, so we need to divide it by 2. So we've got 0.0015 moles of barium hydroxide. We then do N over C times V because we got the moles. So we're going to divide it by C, 0.2, because that's the concentration, which I've circled at the top there. And that's going to give us the volume. Remember, the volume will be in decimeters, 7.5 times 10 to the minus 3. Volume is in decimeters. So as the answers here are in centimeter cubed, I need to times by 1,000 to get decimeters. It's not 75. I need to use a calculator. It's going to be 7.5. Sorry about that. So if you do 7.5 times 10 to the minus 3 times 1,000, the answer is 7.5 centimeter cubed. All right, let's go. 15. Which reaction has the largest atom economy for the production of hydrogen? All you've got to do here is your mass of hydrogen divided by the total mass of the products. So for this first one, we've got hydrogen divided by carbon monoxide plus hydrogen is 2 over 30, and we get 6.66%. B is definitely not the answer because it's like 2 divided by 65.4 plus 71 plus 2, so I'm not going to bother with that one. And then we've got C is 6 divided by 34 times 100, 17.65%. That's going to be our answer, as the bottom one's rubbish as well with a 4.34%. Let's move on. Question 16. Which species is the best oxidizing agent? So which species will cause another substance to lose electrons? So itself gets reduced by gaining electrons. Well, chloride ions and bromide ions can't gain electrons, so they can't make something else lose electrons. They've already got a full outer shell. So it's going to be bromine or chlorine. Chlorine is smaller than bromine, so we have less shielding, so more attraction. So basically, chlorine is more reactive. Yeah, better oxidizing agent. Okay, 17. Which of these correctly shows the numbers of subatomic particles in a 41 K plus ion? That's a potassium ion. It's an isotope, so we can see it's got 41 and 19, so it's going to have, however, it's a positive ion, so we're looking at 18 electrons. We're looking at 19 protons, otherwise it's no longer potassium, and it must have 22 neutrons to have a mass of 41. 22 plus 19 is 41. So the answer is C. That one was nice and easy. 18. After reaction of some zinc metal with excess sulfuric acid, a student collected 40.8 grams of zinc sulfate 0.7H2O crystals. The yield of crystals was 70%. What was the original mass of zinc used? Well, we've been given the actual mass of zinc, hydrated zinc sulfate of 40.8 grams. We don't know what the theoretical mass was, but they've given us the yield was 70%. So we could do yield equals actual mass over theoretical mass times 100, rearrange, and we'll find the original mass of zinc sulfate crystals. And then that's 1-to-1 to the zinc. What I'm doing here is if 40.8 grams equals 70%, what was 100%? So you could work out 1%. I could do it this way as well. If I do it like this, 40.8 grams equals 70%, I can go 40.8 divided by 70 to find out what 1% is, then times it by 100. I know the original of zinc sulfate that we had. Well, I should have made the theoretical mass of zinc sulfate made should have been 58.2 grams. I can work that out in moles, okay, by doing 58.2 grams divided by the MR of zinc sulfate, which is 287. This gives me 0.2031 moles of zinc sulfate is what we should have made. Therefore, as it's 1-to-1 with zinc, I know I also have 0.2031 moles of zinc. Zinc has an MR of 65.4. So I can do 0.2031 times 65.4, and I will get a mass of 13.28 grams. And that tells me that my answer is going to be B. Oh my gosh, We're nearly there. Question 19. Which of these is a redox reaction? So what I want to do, calcium oxide plus silicon dioxide. You should remember that metal oxides are base and non-metal oxides like silicon dioxide, SiO2, are acidic. So this is going to be a neutralization reaction. And then we can go ahead. So I definitely know it's not redox. This is a neutralization reaction forming calcium silicate. But what we can do is we can just check out the oxidation states, and that will tell you if they don't change, it's not a redox. Calcium's +2 in calcium oxide, the oxygen's -2. Silicon dioxide, the silicon's +4 and each oxygen is -2. Calcium's +2 there, silicon's +4 there, and there's 3 -2 oxygens to make -6 to cancel out. That is not a redox. Let's check out B. B, you've got sulfuric acid. Sodium is definitely +1, oxygen's always -2, so +1 for sodium, -2 for oxygen. -2 for oxygen there, +1. Nothing's changing, guys. This is not a redox. Let's go to basically, if nothing has changed in terms of oxidation states or the ionic charges, it's not a redox reaction because things aren't losing or gaining electrons from reactant to product. So sodium's +1 here, it's +1 there. Let's check out the old bromine. Bromine's -1 there, hydrogen's +1, sulfate's -2. Yeah, this is not redox. Let's go down to the last one. It's got to be more promising, eh? Magnesium is 0. What about in magnesium sulfide? Well, it's going to be +2. Why is sulfur and magnesium 0? In elemental states, elements have 0 for their oxidation state. This is a redox because the magnesium has lost electrons and the sulfur has gained electrons. By the way, oxygen can change its oxidation state if it's with something a little more electronegative like fluorine. Right, question 20. 2.40 grams of an explosive J contains 0.473 grams of nitrogen. J also contains 33.8% carbon and 1.14% hydrogen by mass. The remainder of J is oxygen. What is the empirical formula? Oh, blimey, they've given us grams, mass, and they've given us percentages. I need to either work out the mass of carbon and the mass of hydrogen and mass of oxygen, or convert this mass of nitrogen into percentages. I want all percentages. Remember, with empirical formula, you can divide the percentage by the AR, or you can divide the mass by the AR, essentially. So you can either do percentage by AR or mass by AR. It's easier here for me to work out what the percentage of nitrogen is from the total. So I should do 0.473 divided by 2.4 times 100, and that will give me the percentage of nitrogen here. Oh gosh, it's getting late. I'm doing it by 100. Right, let me do this again. 0.73 grams divided by 2.4 times 100. This is converting the nitrogen into percentage just because they've been a bummer and they've given me the other elements as a percentage. So I'm trying to get them all into the same unit. All right, so nitrogen is 19 0.7%, carbon is 33.8, and with empirical formula you divide by the AR, so 33.8 over 12. Hydrogen is 1.41% over 1 because hydrogen's AR is 1. Now oxygen they've not given us, but we can take the 100% and subtract all the percentages of the others. So we can do 19.7 plus 33.8 plus 1.41, do 100%, subtract that, it makes, whack that in the calculator, no, it's not 50, it's 45% roughly 45.08, but that's basically 45. So now what we do is we divide all of these percentage by masses that we've done by the ARs, and I'll get 1.4 for the nitrogen, 2.8 for the carbon. They're looking like they all divide into each other. 1.4 for the hydrogen. 45 divided by 16 is 2.8. Brilliant. Simplify by dividing all by the smallest. So 1.4 by 1.4, 2.8 by 1.4, and you're going to get 1, 2, 1, 2. Now, which formula matches that? So I've got N1, C2, H1, O2. That's not in the correct order. So we've got C2, HNO2, and that is C. Beautiful. All right, guys, we got to be going to the final question. What is the number of atoms in 0.01 mole of ammonia? The Avogadro's constant L is 6.022 times 10 to the 23 mole to the -1. So what I want to do to find out the amount of molecules of ammonia I have, I do moles times Avogadro's constant. If I had 1 mole, I'd have 6.022 times 10 to the 23, but instead I've got 0.01 times 6.022 times 10 to the 21, and that is my molecules of ammonia, I found out. However, each ammonia molecule contains 4 atoms. The question wasn't asking us for how many ammonia molecules, it was saying how many atoms. So we need to times this answer by 4. So 6.022 times 10 to the 21 times 4 equals 2.4088 times 10 to the 22, and that's going to give me answer D. All right, guys, hope you liked it. Hit the like, subscribe, share, all of that jazz. Help pump the channel. Nice one, guys. Take care. Let's get to the marks.
You're still here? It's over.